So, good afternoon, friends. Good day, everybody. And today I want to focus on this topic called instance segmentation based on our experience in implementing this at one of the global top five companies quite recently for a very critical project. And we received appreciation from the team there. And I'm trying to highlight some of the best practices that we used using this open source library called the Detectron 2, which is from the Meta AI or the Facebook. And we found this a very good, convenient open source library to and very accurate to do instance segmentation on different types of use cases, be it manufacturing defect detection, corrosion detection, or let's say some kind of use cases in the biomedical engineering field, right? Detecting microbial colonies, right? All those things. Wherever the objects are very small on the dish and one wants to count those objects, minute objects, the Detectron 2 is one of the best right now. And the advantage is it's open source, it has all the documentation. Right now, it works in PyTorch. It was originally implemented in Cafe 2, and this is my collab notebook to demo the Detectron 2 today. I intend to demo the Detectron 2 by doing a custom training on one of my own data sets and then showing how it can be used with various backbone layer configurations and how the metrics can be checked uh, for each of these configurations, and one can come to a decision which configuration is the best suited for one's own use case. I'd also like to show some demo on running videos of instance segmentation, right? So as we can see, the Detectron 2, basically one of the main advantages is it has various models in their model zoo which are pre-trained, right? And these are uh, based on various computer vision use cases like instance segmentation, object detection, key point detection, panoptic segmentation, and all that. So just by changing the configuration, one can pick up the correct model and use it for the use case, right? So the first step, as usual, is we install the Detectron. But before installing the Detectron 2, here I am installing the PyTorch 1.10 with CUDA support because GPU support is quite important over here. Let me see, I have chosen the GPU, yes. And Detectron 2, right now, the observation I have is it's compatible with PyTorch 1.10, and so I'm installing the PyTorch 1.10 here. Collab by default comes with PyTorch 1.11, so that's the only thing here. And once we have installed this, we are ready to go. We can check out our versions here. We can see that PyTorch 1.10, CUDA 11.3 is installed. So we just import our Detectron to libraries because it's installed now. It should not have any problem. And once we import the Detectron 2, this is based on the Detectron 2 tutorial, collab tutorial, which can be found on their basic page over here. But it has more enhancements. If it was just a collab tutorial, I mean, there's no point showing it over here. There are some enhancements I'm using to do data augmentation, to use different kinds of backbone layers, using the point trained architecture and all that. So that's the purpose here. So as we can see, once we uh, install Detectron 2 PyTorch, we have the correct versions in place. We have a GPU, we have a CUDA installed properly. What we can first do is we can, to see if everything is working, we can download a image from the Coco dataset and just run a instance segmentation on this image without doing any training by using the default model which is available in the model zoo. So you can see the code here, just a 5-6 lines code, right? So the model downloads for a few seconds, and we can check out the prediction using the visualizer tool provided by Detectron. So we can see it has got the person, it has got the horse quite accurately, persons here, an umbrella here, all those things, right? So that's the that's the result of the instance segmentation we are getting by using the out of the box Detectron 2. We can check out how the output looks like. So this is the output which I get by passing the image to the default predictor object from Detectron. Just 4 or 5 lines of code. Here we are using the model zoo, from the model zoo, the instance segmentation model, which is trained on the COCO dataset and uses the mask RCNN family of neural network architectures with 50 feature pyramid networks, R50 FPN. So this is just one liner here to create the model configuration, load the model weights, and use the predictor object with this configuration on the image that I have. So this IM is the image which I just downloaded and read it using OpenCV, right? So we can see how the outputs here looks like from Detectron. So it has basically the grid classes object. So the outputs instances are the instances, are the segments which the algorithm has found out in the image, and the class IDs are the class IDs of the object is that's found out in the image, right? So we can check the COCO dictionary to find out what class IDs these are, and it is basically using that to generate the labels for these class IDs over here, right? We can also see that the B boxes it's giving, the boxes, which is the object detection boxes, right? And it'll also have the segments inside it, which I'm not going into it right now. I'll go into it later. These are the corners of the boxes of each of these boxes, the top corner and the bottom corner, the XY coordinates, right? So we can check up the outputs instances in total, and we can also will also see the segmentation masks in the result. Right. So these are the pred masks, which we'll have to, which is basically generating this instance segments on the image. Right. So we'll see this in little more detail later on. So now that we have done this, what is the process to train our own model to use the Detectron tool? Quite obviously, when we have a project, we will not be using the tool to detect persons or horses. We will need to detect something of interest to the business, right? It could be defects on a steel plate, it could be corrosion spots, it could be anything. So how do we label and annotate these images to for Detectron to be able to use it easily? So one of the things to understand here is the Detectron 2 uses the COCO format of annotation JSONs, and this can easily be generated using many open source tools. For example, one of the tool is a VIA annotation tool. It's from the Oxford University, the VGG instance annotator tool. So when we open it, we see a page like this. We just click this, and it has a annotation defined with a swan. We can see this, and so we just have to upload our images, annotate this, and then say export annotations in COCO format. That will give me a JSON format. So how do we do this? I'm removing these sample images, which is provided for illustration. And what I can do is I can use my own files here. So for example, I have downloaded some Rust images from the internet, corrosion images, right? And these correlation images I'll try to now annotate. So for example, if I take this image, I must say this is a correlation spot. So this is my correlation spot. This is another correlation spot. This is another correlation spot, right? Another is here. So this is the way I mark out the objects I want to detect. And once I do this, I can just say annotation, export annotations, COCO format. So it downloads the annotation. We can see that annotation in any tool. So this is annotation. How does this annotation look? We can see with the help of an online JSON viewer and put our JSON over here. So we can see that it has many images. All the images I have uploaded, it has become part of this. But the annotation objects, there are 6 annotation objects. These are the objects which I just annotated. So we can see that there are 6, 1, 2, 3, 4, 5, 6. That's what it's saying. And these annotation objects basically will point to the image ID. So the image ID is 3. That is the image ID. This annotation object is pointing to. That's how the COCO format is. Since I annotated only on one image, all these annotations will all point to image ID 3, as can be seen here. What's also important is the category ID. Category ID is 4, and by default it will say this is an unknown category. So it will say unknown. So we just have to edit this JSON and change the name here and name the object that we are trying to segment, in my case corrosion. So all these annotation objects will be there one after another, and they will point to the images which we have in the image array, in the image node. So that is how the COCO JSON works. It's a bit unconvenient, I would say, because the images with the annotations are not in one place. We have an array of images with the image IDs, the image widths and heights, and then we have a so each image has an image ID, and then we have a array of rust2.jpg. So this is the one I probably rust2.jpg. So this is the image ID. ID is 3, but here the image ID refers to this array position ID number 2, and that's what the annotations are saying, that this is belonging to image ID 3. No, it is image ID. Image ID is 3. So if we go to image ID 3, we see that it is this one, image ID 3, rust2.jpg. So all the images are present in the images array, and all the annotation objects will be there in the annotations array. And these annotations also has something called the B boxes, which is the rectangular area, or in this case it's a ellipse I have taken, but it has generated this B box coordinates. It's not going to be useful here. It's what is important here is the segmentation node, which has all the pixels which are there in that segmentation. So when I say segmentation 0 has all these numbers, it is basically the pixel coordinates for this segmentation, for this object, which is this object. All the pixels that come within this will be there in the annotation object. So this is how the JSON looks like. And so I have just prepared this on a few sample images which I have downloaded from the internet. to detect corrosion, and let's see how that works. To reduce the time, I'll upload these images along with the train and test JSON that I have. So first I'll upload the images, and then I will upload the train and test Coco JSON. So I'm done kind of uploading. So now I can start my training. So the train JSON is on the basis of my train images, and test JSON is some images I keep aside for testing when I'm done with the training. So the first step is basically we register the train data set, and here, since we have a Coco JSON directly, we can directly use that in our training process. So there is a step called registering the train dataset where we point to the Coco JSON, which is the train Coco JSON here. And so it says it has loaded 21 images in the Coco format. So the one other thing I wanted to show here is this particular train JSON, the category ID. Uh, I should point out that I'd like to open that in the JSON viewer tool. So I'll take the test JSON since this is a little smaller here. So I come here, I have all these annotations here and the categories. So here I have one category, which is my category called corrosion, because that's what I'm trying to detect. And the ID is 4. And this is the ID which is there in all my annotations, as can be seen, category ID 4. If I am detecting multiple types of objects, then there will be multiple categories here. Let's say in one of the projects that we did, we were trying to detect two types of things, two types of objects. So in that case, there will be two category IDs, maybe 3 or 4 or whatever it may be, and then uh, they will be referred to here in the annotations, in the segmentation objects. In this case, the category ID is 4 and is referring to corrosion, and the image IDs are interlinked over here. So these are belonging to image ID 1, this is belonging to image ID 3, and all that. Test coco.json. So once I have this, I have registered my train data set, I have registered my test data set. One thing that we normally do is we check up if my train data set is loaded properly by doing visualization on the data set. So what we do is we create a dictionary by doing a dataset catalog.get and give the dataset name, and using that dict we basically uh, get the file name, and we basically read the file because the dict contains a file name based on the image ID, and we get it, and we can check up how that dictionary looks like by printing it out. So it has various nodes, key value pairs like file name, image ID, and all that. So based on the file name, we know the files are present. We just read it using CV2 and visualize that along with the annotations. So let's do that. So we can see some example images that we have annotated over here. So it is showing that the corrosions have been annotated and they are visible. They have loaded properly. This is another example. This is another example. The corrosions have loaded and the annotations are loaded properly. They are visible in the correct place as it was annotated. So this is my train data set. Now I am using the I'll come back to this later. Now I'll be using the instance segmentation models from the Detectrons model zoo to train my custom model on corrosion. Now here is something important. Here what we do is we have a few different options. The Detectron model zoo basically provides pre-trained models from the mask RCNN family mainly, and it provides other architectures also, which I'll show also here quickly. But mainly the mask RCNN, and some of the important models there are this R50 FPN, R101 FPN, and X101 FAN architectures. So all these backbone layers are interchangeable, and just by using a configuration parameter we can change the backbone layer configuration of the model we are trying to instance segmentation model we are trying to train. That's one of the biggest advantages of Detectron 2. It's the configuration driven approach. One can change the backbone layers very easily, as we'll see here. So out of these, we are now going for the mask RCN and R50 feature pyramid network. So we can see here, I'll comment out this because this is for a later exercise where we'll use a point trend architecture. Right now, we will use the Detectron architecture, the mask RCNN family. Right, yeah. So we say config dot merge from file modelzoo.get config file, and we just mention the architecture name over here, the mask RCN and R50 FPN. If I'm going to use R101, a much more complex architecture, I can use that. So these are basically complex, more and more complex architectures. In most cases, the R50 backbone is preferable as it trains and infers more quickly and requires less resources. But for more complicated data, or where we have lots of data, the X101 and R101 models might do better. The benchmarks are given in this link. One can check it out. And all these benchmarks are given here. What was the AP values obtained on the COCO data, on the based on the mask RCN and models which it provides, the Detectron provides. So all these benchmarks are available here. One can go through it. So coming back here, so once we do this, that's all. We mention our data set, trained data set, which we registered in the previous step. We we do few things where few parameters are needed here, like the learning rate, the number of iterations we're going to run. We keep it at default provided by the Detectron, which is the default values 300 iterations. Num classes is one. We are detecting only one object, which is corrosion. So we need to use this num classes. And that's all. We create our trainer. Now here is a small enhancement which I'm using here, which is not there in the Detectron tutorial. I'm using a custom trainer rather than the default trainer. And why custom trainer? Because the custom trainer is using a built train loader, which is basically using the mapper, which does a augmentation, image augmentation on the fly. Now, this is a best practice to use image augmentation. Image augmentation for instance segmentation is a different uh, area than normal image augmentation. I talked about image augmentation in one of my previous sessions, which was basically how to augment images for image classification. But we have to understand for annotated images, when we are doing instance segmentation, the image has to be augmented with the annotations. So the annotations and the images have to be augmented together. That's very important because I can't expect that I augment the images and then ask the annotating team to annotate those 1,000 augmented images, increasing their work. We can't do that, right? So the annotated images, as it has been prepared, has to be augmented. It has to be rotated, resized, flipped, but along with the annotations, image annotations, that is these annotations. So if the image is rotating, this also has to rotate by a equal value, this annotation object. That is important. That's why we need to use the Detectron transform here. We can't use a normal annotation library. So that's what we are using. This T is basically a Detectron transform. We can see here it is being imported here, Detectron data transform, and one can read up about it. the detect on data transform is being used here to do the transforms, and this is the way it has to be done. So the custom trainer is using a built train loader, which basically uses this configuration and this custom mapper. So that is important here. We are using that to do data augmentation with the annotations, and let's start the training. Custom trainer is not defined. I didn't run this cell, skip this cell, so now I'll run it. I'm doing this training live because I have, with the GPU facility, 300 iterations is going to go very fast. As you can see, 1939 going very fast, 59. So in a minute or two, 300 iterations will be done, and we can see the results. Halfway through, we can see the loss coming down slowly. 200 iterations done. So while this goes on, I'd like to draw attention on this labeling and annotation tool, the VGG instance annotator. Now this is a freeware tool, and what we have noticed is a lot of companies, they have security restrictions. They, because the data they have is sensitive, they cannot upload this data on a freeware tool like this. So it's very important one uses a proper tool in a proper environment to do these annotations. Second important, there are multiple tools over here like VGG instance annotator, label me, CVAT. The important considerations are that these some of these annotations, they should be editable, right? They should be exportable in the proper format. They should be in a secured location. I should not have to go to open source site and do this. Second thing is, as we can see, we are downloading this JSONs and uploading it into another environment, which is also a bit of an inconvenience when I'm doing this again and again. So how do you overcome this is something I'll talk about towards the end of this session. So my training is done, 300 iterations, and I can see the result on the tensor board if I would like, how the loss is coming down and all that. But I would be more interested to see how the results look like with this model. So I load up the model weights, so I can see that I'm not interested in the data time and ETS seconds, but I can probably see the loss, how it came down, total loss. So I can see the total loss came down quite nicely. So I load the model weights and I use a threshold of zero point 0.5, which is the probability value beyond which I consider it a correct prediction. Use that. And what I can do is I can use the training data to do some sample visualizations of the results. So I do a predictor. I use a predictor object to generate a prediction, and I use the detectron visualization tool to do the visualization. So I can see some objects here with lots of correlations identified. Let's quickly turn to the test data, the dataset DICTS test, which is obtained from the test JSON which I have uploaded, and we can have a look at it, how the dictionary looks like. Basically, it has all these annotations, segmentations, and everything for each of the images we have in the test data set. So that is the data set we test. We use that to generate our predictions and see how that looks. So we can see this is the first image, and we can see that this particular image, for example, we can see that it has picked up the correlation. This is based on this image, just 46. Let's look at the image. So this is the image. It has picked up some additional areas, which is possible because my training data is not very accurate right now. This is based on the rust.5.img. Let's see. This one, it has picked up pretty well the correlation areas. Rust6.jpg has picked up the correlation areas very well. So we can see the results of the prediction on some sample images. With few, the advantage of detectron is what we have seen is with few images, with few labeled images, few annotated images, it start producing good results which can be presented to the business. Of course, if one needs very accurate results, one has to use more data. So the important aspect about this is how to use the augmentation while doing a instance segmentation training. In case of detectron, we can use the detectron transforms, and also how we can how we can annotate and label the data using various tools, and export the annotations in a Coco JSON format, and with a few lines of code we can train the model and see the results. We can evaluate the performance of this model on the test data set. So we can check what is the segmentation metrics coming out of it. So for example, we can see that the AP50 metric is 57%, right? And what is the AP50 metric is something which is defined here. The average precision AP50 means AP where IOU is equal to zero point 0.5. AP at IOU equal to zero point 0.5. The Pascal VOC metric. What is IOU? I think the best way to learn IOU is not to read anything but just to look at this images coming up with IOU on Google. Just type IOU score, and one can click on the images, and one can see how it is showing exemplifying with images. So the area of overlap by the area of union, area of overlap between the predicted segment and the actual ground truth segment which was annotated. What is the overlap and what is the union area? So when we divide that, we say this is the ratio intersection over union. We can see the example here. This is not good, this is good. IOU equal to zero point 0.7, and this is excellent sample IOU scores. So when we say IOU is 50% is my minimum requirement and consider those as true positives, what's my absolute, what's my precision, average precision? So that's the measure which is being used here, AP50. There are other values, like we can change the thresholds and get the AP value at various thresholds of IOU and average them. That's also possible. So whichever metric one is interested in, one can check. So in this case, for example, I am checking the AP50 and the AP, and we can see that the AP50 is basically, now these are again two different metrics, one for the bounding boxes, which is the rectangles, and one is for the actual segmentation. So if you are interested in the segmentation, we have to look at the segmentation metrics. So that's why I'm using the segmentation metric for AP50, and I'm putting it into my own metrics JSON because I may not be interested in all these values over here, which has been given by Detectron. So I take the segmentation AP50 and I can record it as I keep on iterating with various backbone layer configurations and take the result which gives me the best AP50. That's a point over here. So one more important thing that I have come across is many a times the business is not really interested in the AP50 metrics. They're mainly interested in the count of the object. So let's say if it is a steel plate with number of defects, am I counting those defects correctly? That's all they are interested in. Or it could be something else, could be microbial colonies on a plate. Is the count coming correctly? So in that case, the segmentation matrix is not of importance. Secondly, what I've seen is business generally don't want to understand complex terms like AP50, IOU. They like simple terms like give me the counting accuracy. So in that case, we can do a little bit of a uh, Python code to come up with those accuracy metrics. These are called MAE and MAP. MAE is mean absolute error. So I'll show how to derive that. So what I did is I did a little bit of JSON reading from this test coco.json. So what I'm doing is basically I'm getting the annotations and the images and I'm taking a sum. So as I said, the test coco.json is basically we can see the annotation objects here. So these annotations, how many annotations are there for each image? I'm summing it up. So there are 4 images. So some of these annotations are for, so for example, the first image we have image ID 0. This is image ID is 1. So image ID 1, we have one annotation, we have only one, right? So that is what is coming out here as well. Image ID 1 has number of annotations. Image ID 2 has number of annotations 7. So let's check that. Image ID 2 has number of annotations 7. So this is image ID 2. This is image ID 2. This is image ID 2. Image ID 2. Image ID 2. 2, 3, 4, 5, 6, and this one. Next one should be some other image ID 3. So I have 7 annotations belonging to image ID 2. So basically all I'm doing is I'm combining these elements and matching with the image ID here, as we can see. So I do a data frame with the images, the image node. I do a data frame with the annotations node, and basically I take a sum with the image ID, group by with the image ID. And once I do that, basically I merge the annotations and the images with the image ID. So I have this. Now this is my ground truth, which is a count of objects which I have, which I have labeled. What is that I have in the actual prediction? For that, I need to create an array while doing the prediction. So what I can do is I can create an array over here. 16, So I'm going through the test images, so I can say image id and equal to red effect. And what I can say is for each image, the the output instances is basically the number of defects. So I can say image. I want to match with the image ID, so I will match with the image ID. I think there will be image ID here. Yeah, definitely. That's what I have in the test JSON. I know that. And I will, here I will, so let's see. Yes. So I have these two ads now. Now I'll have to create one data frame combining these two and get the MAE matrix. So I create a data frame with the image ID and pred defects, and I say df image ID equal to image df. What was the name? Pred defect. I can check that. This is, let me call it pred data frame. So I have the image ID, and for each image ID, how many defects were predicted. So I have it. So now it will be a simple matter to combine these two. So I can say df image nose and pred equal to, I can merge this. So on the one hand, I have annotations, the ground truth, and on the one hand, I have the predictions, just accounts. So on in this, it's known as ID. So on the left on is ID. In the right hand, it is known as image ID. So let's see the DF image and yes. So I have this image ID one. It has one annotation, but it has predicted four such correlation objects. Second image ID has seven annotations. It has predicted 17 such correlation objects. Speaking up more due to some reason. Okay, so whatever it may be. So that's what now we basically need to consider for our MAE matrix. And a simple lookup of the MAE matrix will show what it is. It's basically mean absolute error yi minus y hat I 1 by n. So we can implement that over here. I don't need so many columns. I'll reduce some of these columns. I need image ID. I need number of annotations. I can keep the image file name if I want to check anything. And I need the pet defects. That's all I need for now. Make it a little more cleaner. That's all I have. And now I will calculate the MAE matrix. So by definition, I'll say sum is equal to 0. This is my sum of absolute deviations. So for I in range len this particular data frame, this is sum plus equal to absolute this data frame number of annotations minus this data frame number of defects. Finally, I can say sum. Let's see if the sum is coming correctly. Oh, I didn't give the I over here. Okay, so I can see the sum is 37. Yes, I can check it up 3, 10, 11, and 13. It's correct. So my MAE is nothing but sum by len. I can find out the MAP in the same way, right? I can do again the MAP calculation. The only difference in MAP is I take this value, the absolute difference, and divide it by the actual value, and then multiply this whole thing by 100. Keep multiplying by 100. So I take the percentage deviations, and MAPE is then again the sum by the number of elements we have in the data frame. It's about very high because we can see with our own eyes that where there are 7 annotations, it is predicting 17 such segments. So model needs more data to train, but this is how to calculate the MAE and MAP. Another best practice which I have seen is to calculate the MAE or MAP in various count ranges, particularly the MAE. So business might want to know what is the mean absolute error for those images where the actual number of annotations is 0. These are basically the negative samples, which means if I have steel plates on which I'm counting the defects, now it should not be that on those plates where there are no defects I'm predicting a lot of defects. So that means one has to spend a lot of time to correct that. So whatever productivity I'm gaining by finding these defects on the defective plates, it is being more than offset by correcting those cases where there are no defects and the model is predicting defects. So business also sometimes wants to know what's the mean absolute error separately on certain counts. For example, the count 0, which means what's the mean absolute error on the negative samples. So one can simply extend this. So one can say, for example, I can find out what's the MAE for count 0 by just taking the sums for count 0. So if, just have to add a if clause here, if this is equal to 3, so I'm trying to see the MAE for those samples where the count is 3, then do the sum. And I need to have a counter as well, for I need to count those, counter equal to 0. So counter plus equal to 1 for expected in and block. Okay. Sum by counter. So MA3 here will be 12. So I have basically a deviation of 11 here, deviation of 13 here. 13 plus 11 is 24. If I divide it by 2 samples, it's 12. So the MA value for where the count range is 3, the count is 3, I can do for different count ranges as well. So I can say, give me the MA value for where the defect count is in the range of 1 to 5. So just changing this if clause will do that. So this is a very simple matrix, MAE. And MAP, that difference is MAP we divide by the actual number of defects. Why this is important? Because when I am having a count of 100, a deviation of 1 is less significant than when I am having a count of 10. So MAP takes care of that. MAE is just the absolute deviation. It doesn't consider the actual count. MAP divides by the actual count to get a percentage deviation and then takes the average of that. And that also can be easily be found out from Google MAP formula. So actual minus forecasted by actual, keep adding this and then take the average. So the reason I say this, because many cases in segmentation scenarios also, the business may be interested in more in the count, the accuracy of the count rather than the segmentation area. So one case where the business may be interested in the area is definitely the corrosion, where the area is important. In some other cases, let's say defect detection or microbial colony counting of that, right? There the count is important. So in that case, the MAE and MAP can be found out like this. So having said that, I would like to now show some advantages of using the detectron. So for example, how the uh, backbone layer, so not the background, the backbone layer can be changed just by changing the configuration. And not only that, I can start do incremental training based on the previous model I trained just by changing this line to saying this line. So I can say take the model which was there before and now start training on top of it. So this is a simple one-liner change by which I can do incremental training, which is one of the advantages of deep learning, which is not possible in normally in machine learning. In machine learning, one cannot do incremental updating of the weights. One has to use all the data set from the beginning and create a new model. But in deep learning, it's possible to incrementally update the weights. So that also in Detectron, it has made very, very simple, just saying model.weights equal to my model file which was there, or I can start from the model zoo. So in this case, I am doing on the R101 FPN, and I just change this line. That's all. Rest of my code remains the same. I'm going to train with the R101 FPN. It downloads a model and we can see results. While this trains, I would like to discuss on another important aspect of Detectron, which is the point train technology. So the point trained is a new architecture from Detectron, which is supposed to be more accurate. This is a point trained page. It's a point trained page within the Detectron 2 projects. Point trained is an image segmentation model which is based on this paper. The paper link is also given here, and the instance segmentation results from point trained and detectron and the detectron 2, which is basically the mask RCNN, is compared here, and one can see in case of detectron 2 the instance segmentation is good, but some of these areas we can see that it has done averaging out. But in case of point and we can see the fingers also are clearly visible, the corners are clearly visible, all that. This is the detectron site. I think I should give a link on the point trend. I think I would have given here. Add this link also over here. So yeah, the point trend is also another important thing. One should try out one if one is looking for very high accuracy of instance segmentation, and they also have their own pre-trained models which is using this various backbone layer configurations, and one can feel free to use any of these, right? So this point train tutorial also provided in collab, and one can look at it. I remember one image here. Yeah, so this is the point trained. So the point trained result of segmentation, the top one, and the same result with detectron. You can see this is little more accurate. So how we can use a point trained instead of detectron to backbone layers, we can see that as well. We are almost done. 259. Quickly check the accuracy of this, how the AP50 metric is coming. It's done. So we can load the weights from the model file created, and basically we can use our test data to basically visualize some of the results. See, this became much better now. As we can see here, this image rust46.jpg. This was the original image, and we can see here now the segmentation quality is much better with R101. So that's the point I was saying. Even this one, the previous one, the lower portion was not being obtained, but now we can see it is being obtained, right? Right. So this is as simple as that, and I would like to, show how I did this 3 years back in my blog. So on corrosion detection, this was the blog post I wrote 3 years back, and I used the TensorFlow object detection API for doing the corrosion segmentation. The first part is on image classification, where I'm classifying an object, an image, if it is having corrosion or not having corrosion, which I discussed in one of my earlier blogs. The second part is on the actual segmentation or delineating that corrosion, which I have given an example. And you can see the number of steps here much more complex. It is, I'm using the SSD mobile net over here, and finally I'm getting this boxes where the corrosion is detected. It's not segmented as yet, it is detected. So here we can see with much less code, we have been able to segment out the corrosion spots, right? Using the, and we can even check the metrics, how it's coming with the X. It's coming 56, AP50 is 56, but this is the bounding box and this is the segmentation, yes. So it's increased slightly. We can see, I think last time we got 53. We can check these also, MAE and MAP. create the combined, and then finally we say what is the MAE. It's reduced 4.25 MAE. Count range 3, reduced much, MAP reduced. So we can see clearly how using a better backbone layer helped in this case. And my only change was just a one liner change here, changing the name of the model. So that is the advantage of Detectron. We can use a point range just by using these lines, point range, and we'll have to basically git clone the Facebook repo because the point range uh, configurations come as part of that repo. So we'll have to load it from there. So we git clone it, and then we say instead of the Detectron model zoo, we use the point range model zoo, and we add the point range configuration. So it's very easy to use the point range over here. So I'm using the point range, and this is one thing that I have to give additionally. That's all. And here I can use a custom trainer point range. Custom trainer point range is the same as the one I was using here, just that it doesn't need all this transformation of the JSONs, needs only the transforms, which is doing the image augmentation. That's all it needs. So once we do that, we can train this using point range. So while this point range training is going on, let me discuss some of the issues faced in industry that I've seen. That a lot of the times we have seen that there are lots of process bottlenecks in industry. I've seen in one case one such project on instance segmentation, just one use case. It's going on for more than 1 year. There are lots of security constraints. For example, how to do the annotation and labeling, how to use the annotations, how to export the annotations, how to use it and train a model, how to do model retraining, how to use a continuous feedback loop to use the corrected annotations and and feed it back to the training process, make the model more accurate, how to report the accuracy metrics using the MAE and MAP. All this takes a whole, sometimes it's taking month after month, and it's running into year, even more than a year. I've seen it. So that is where there is a huge need for a single platform which can do all these things in one place in the area of computer vision and instance segmentation. And that is where the company that I have joined recently, the startup company Looper AI, we are actually aiming for that. We have a very good annotation platform, and some of the best practices of the annotation platform that I was trying to say is, you can see here, for example, in the VGG instance annotator, I can draw the ellipses, I can draw the circles, but some of these I cannot draw a free form object over here, and that could be a need in many situations. It may not always be an ellipse or a circle, because we can understand the machine learning model will be only as good as the annotation data, as the input data provided to it. So if my annotations are not correct, it's only approximate with an ellipse, the result will also be not good, right? So we need to do free form annotations, and that's a problem with this tool. It doesn't work very well. I was trying it the other day. Most of the tools have some limitations over here, and the second biggest limitation is I have to upload my images to an open source site. Most customers are not willing to do that because of the sensitivity of the images. So that is why, this kind of a platform that we have, which is a one single platform to do everything, entire set of processes, is very, very important. So let's see how this looks on the test images. The point range, we can see this is also pretty good, right? Check even the metrics. It's diminished due to some reason, but whatever it is. So these are the things that can be done. And finally, one may say that I am doing everything on Collab. How do we expose it as a REST API. That's very simple. I have this REST API running here. We just do the same things. There's just a few lines of code again, running it in a REST API, running the detectron. This thing. I'm just returning a hard coded image because I don't have the same environment. So that model will not match with the environment I have. But once I do this, I start up this, I can just go to it in my local host. So this is my Swagger API predict image where I can upload an image, but I can't view the resultant image. For that, I can start a Postman, and in the Postman, I can give this image and see the result immediately. So this is a predict image URL which I have exposed using Fast API. So I say file, my body, so not the param, sorry. So I say file, I select my file. In this case, I select this one, send it, and I get the prediction here. So this is what it is. Very simple, using Fast API to expose it as a REST service, and this can be easily put it in Docker container and deployed on the Azure portal. So those are some of the best practices I wanted to discuss today, and I how to use this entire process of annotation labeling, how to use change the backbone layers, how to use the various parameters like learning rate, like the number of iterations, how to view the results on the tensor board, and how to check out the metrics and use metrics which are easily inferable by the business. This is very important, and I remember in our last project, the business was so adamant to have 97% and plus accuracy. So it's very important that we check the metrics properly and report the correct metrics to business. Use a different architecture options behind in the background, the neural network architectures. It could be point trend, it could be mask RCNN, and use the best option which gives the best metrics which is needed by the business. And all this within a quick setup time. We can extend the detectron to do detection on videos, and here's something from my company website which I can show. This is a detectron detection we did on videos. We can see a mica sheet rolling, and these are the blisters or the defects, and we have trained it on a sample video, and we can see that it's picking up the defects quite well on a running mica sheet. And we can attach any sensor to it, and we can attach it to a alerting system to alert the operators that the defects are coming, right? So this also works quite well. And recently Facebook has come up with something. Meta AI basically has come up with a model for the detectron 2 which makes it possible to deploy the detectron 2 on mobile devices. It's called the D2Go. So somehow we found there is a little bit of a issue with exporting the detectron 2 model as a .onnx format. We had some issues. I'm not saying they're not resolvable, but it's not very simple also. But D2Go is the production ready software system from Facebook Research, which supports end-to-end model training and deployment for mobile platforms. So this is a very good blog post from Gilbert Tanner, who is one of the recognized experts on this. Given the link to this, and using this, much more trimmed down version of the Detectron 2 model can be used to deploy it on the mobile devices. So with that, I'd like to end my session today. Thanks. I hope it was useful and it gives some ideas. I also wanted to add this part quickly. So sometimes what happens if you have multiple objects, multiple types of objects on the we are trying to segment. Segmentation algorithm may not give good results. It gives good results when there are maybe one object or two objects. When I say object or two objects, not the count, it's the type of object. So in this case, we have one type of object, corrosion. But if I want to detect more than one type of object, maybe different kinds of defects, right? I need lots of balanced data, which may not be possible. So in that case, one strategy we have used and has given us good result is basically cropping the images based on those segmentations and then running it through a classification process. And that can be done very easily using the output instances which Detectron provides, using the PredB boxes, and creating a cropped image array which gives the XY coordinates of the top and bottom corners. And using that, I can basically crop out an image easily. And so this is my image. For example, I'll generate the prediction 6. So I'll do the create the boxes for this, and then I can see that this is my original image, and I can see I can create the array of boxes, and I can crop the images. So this is a zeroth box. It's actually basically picking up the corrosion here. Let's see the boxes how they are. This is the round one. Let's see, two. So this is this part, right? Like that, the various areas can be cropped out from the image, right? And we can then use that cropped image even for further classification process, which is a combination of segmentation and classification. A combination might give the best results in many cases. With that, thanks, and hope it is of use to some data scientists who are starting in this field. Thank you.